Okay, I guess it's just a speaker. So once more, I'm Roland Haas, and I'll give you the customary introduction to the Einstein Toolkit, basically what it is about and what's the philosophy behind it, and a little bit how you can get involved in it if you want to do so. So this talk isn't just by me, but this is a regular talk that we give very often. So there's a lot of authors, different people have given the same talk, and we try to keep track of who contributed to that. I'm just the first one because I'm giving the talk. Steve gives the talk, he's the first one. If Peter ever gives the talk again, then he's the first one. So this is how this works. And with this, let me see. Let me kind of give you not the high-level overview, what the Einstein Toolkit is. So the Einstein Toolkit is a collection of software components and tools to simulate and analyze general relativistic astrophysical systems. It is freely available, free as in beer and free as in speech, from the Einstein Toolkit website, www.einsteintoolkit.org, which you probably are already familiar with. And thankfully, we are also supported by grants by the National Science Foundation. I think there's one missing. At different institutions, one of them is RIT, and then there's about 4 other institutions that are involved in this. So it's a multi-institutional, multi-year effort to keep this thing running. The Einstein Toolkit hopes to provide state-of-the-art tools for numerical relativity that are open source. It doesn't itself necessarily try to develop these tools, but instead tries to collate them and provide them to the community. So if there's a tool and a code that works, that has been proven to work in the real world, then this is something that the Einstein Toolkit might be interested to see. Would you like to have this created by us, made it publicly available? And if there's things that are being developed by members of the Einstein Toolkit, that's in some sense separate from the Einstein Toolkit itself. So this is how the idea works. Currently, at least according to our website, we have 402 registered members, persons that have said, I would like to be mentioned as a user of the Einstein Toolkit on your website, from about 282 individual universities and from 49 countries. So that's fairly large, and it's ever growing. At one point, we'll probably have to prune this down a little bit and make sure that people that we know have moved are moved to their proper locations. But this is it. So it's still active, and there's lots of people in there. There have been about 400 or so publications since its inception, and about 57 theses have been written building on these components. And the theses, these are the ones that we know of because somebody told us, I've used the Einstein Toolkit in my thesis. So there's probably more, but these are the ones we have proof. The nice thing about this is that we have regular tested releases. So every 6 months, there will be a new Einstein Toolkit release where we have incorporated all the bug fixes that were reported, have made sure everything still works, and you can then use that. So there's a nice cadence that you get a code that's relatively up to date, without being something that constantly breaks because you're sitting on some development version. That has been a nice way for us to do things. We do offer user support through various channels. There's a weekly phone call, there's a mailing list, there's a chat channel that you could use, and there's these conferences as well. So that's kind of how it's organized. Now, what can you do with the Einstein Toolkit? So science-wise, it comes out of numerical astrophysics. Traditionally, this meant initially black holes, comes out of the Grand Challenge. Then neutron star mergers as well, very interesting right now. And then things that kind of go along with that, supernova simulations can use some of the same facilities as in particular neutron stars, and general relativity is important. Accretion disks around compact objects, be that neutron stars, be that black holes, is very important now and is done by various groups in various shapes and forms. But then also things that are, I wouldn't say less traditional, but maybe not so directly tied to the current observations. Say you can simulate boson stars with it. You can look for things that aren't quite GR anymore, hairy black holes or things like that. Also cosmic censorship. So it is very flexible to do different things. And on the right, I've just shown a couple of pictures from publications that have used the Einstein Toolkit, just to show what you can do with it. So as far as the releases go, we just had an Einstein Toolkit release, the Schwarzschild release, named after Carl Schwarzschild, the Schwarzschild black hole. That's the 26th release and was released on May 24th, 2023, with 2 release managers this time, Leo Wernick and Sam Kapp, both of which are here. And we are very thankful that the 2 of you went through the effort of doing this. It's quite a bit of work, so we're happy to have you spend the time and contribute to this. The nice thing is that this is the first release where the release managers are actually not Einstein Toolkit maintainers. So that's good because it means that it's not just the old guys that do this thing, but we are managing to get some of the younger persons involved in this, which is good because it sustains the framework. Kind of the new things that we have here is that for the first time, we'll have an improved Slurm-based multi-node tutorial server that Steve has been working very hard, and that you'll see later on in this workshop, and that has been a game changer for us. For the first time, nothing has broken when we gave these tutorials, so we're proud of this. Other things that are maybe important to mention is that we have a couple of new features in there. We've got a reader for the Fuka initial data code by Samuel Tuttle, whom I saw somewhere out here, I guess, which gives you access to a modern initial data code that you can use to produce initial data for the Einstein Toolkit. Also to punctures binary black hole SF is present. That's another initial data code, more specialized for scalar fields around a single black hole. That goes towards looking at things that are not just relativity anymore, or not just Einstein's relativity anymore. And that's part of the Kanuta framework that has been part of the Einstein Toolkit and has been providing these sorts of functionality. So nice to have. And then we have updates and improvements to other things, to the Baikal evolution code, to the particle tracer code, and to the Qubit visualization toolkit. So there's a steady progress in these things that are going in. Right. So as you can see, this is a community effort, and to some degree you might ask, well, why do you want to go through this community effort if it has that much overhead, right? We need to find people who are maintainers. We're basically always working towards the next release. Somebody has to maintain these tutorial servers and all of these things. Why would you want to do this? Wouldn't it be so much easier to just do your own thing at home without having any interference? You can do exactly what you want and nothing else. Well, trouble is, we are facing some computational challenges here. So if you're the single green dot over there and you're working all on your own, then this is a hard problem. It's not so easy anymore to get your work done. You really need somebody to help. You need a team of persons to do that, because as one person alone is unlikely to be able to do this. And to some degree, this is due to the nature of our computation. General relativity is complicated. It is not an easy theory. You can do very little things by hand on a piece of paper. You need a computer. This is a computer, and it was state of the art a while ago. It isn't quite sufficient for what we want to do anymore. We need bigger computers. Bigger computers are more complex and therefore more difficult to handle. They're also more heterogeneous. It used to be a couple of years ago that the only thing that you have to worry about are Intel CPUs of the 64-bit variant. That was great. Everything was the same. You didn't have to worry much. Nowadays, this is different. At the very least, you've got Intel CPUs and AMD CPUs, which are slightly different, not so much. But then you've got these ARM CPUs that are coming in there, which are very, very different. Need different approaches to get good performance out of them. And then on top of that, you have not just the CPUs, but you also have GPUs now, which actually are where the big computing power is by now in the bigger clusters. Both from NVIDIA, these are the traditional ones with CUDA, but also AMD now has ones that are competitive and are used in most of the DOE big machines by now. So if you're going to a really big supercomputer, in the US at least, you will have to use these AMD GPUs. Right, so what do these things look like? This is an actual supercomputer nowadays. This is a frontier system at Oak Ridge National Lab, and it's one of the biggest one, and I guess it's one of the first real exascale systems that people are actually owning up to. And this is what you have to run on. You can see this is a fair number of compute power that sits there, and just by the amount of hardware that sits there, you can see that this is not going to be so straightforward to use. Right. So then, what are the challenges? So we want to simulate cutting-edge science. We want to make use of the latest numerical methods as they are being developed by researchers in various fields. And we have to make use of the latest hardware. That means we have to make efficient use of cache that's present in these systems, which is a problem. We want to vectorize our code to make sure of SIMD instructions that are the way to get good performance out of these. We want to use accelerators, GPUs of various sorts, and other types of accelerators as well. We have to scale to many cores on a single node, which is troublesome occasionally. And then we have to scale from one node to many nodes as well, which means we have to use interconnect efficiently. Algorithms, and that all is a formidable challenge to get things right. So it means that you require experts, not just from one field, but from many disciplines that have to work together. You don't need just physicists that can maybe implement the algorithm, but you also need computer scientists that know the best way of handling a communication algorithm across multiple nodes. You may have to talk to vendors actually to find out what's the best way to use the accelerator hardware. So all of this needs to be done, and it's not something that a single person can do. The way to do this is to really design good data layouts and APIs to let the individual pieces of your code work together well. And that's kind of what the Einstein Toolkit aims to provide. So there's other things. You want to ensure that your code actually produces the correct answer, preferably. That is easy if you have smaller modules that you can test individually, so that if there is a bug, it shows up on a level where you can understand where it's coming from, and not after many, many steps and you don't know where the error is coming from, just that the answer is wrong. So it helps then if you have a design and implementation that's somewhat carefully thought out of, and that helps if you have a bit of experience. So if you've done this a couple of times and you've seen a couple of broken attempts, you're probably more likely to implement a good one than to start from scratch having never done this before. So you kind of want to have a bit of both. Right. So how much time do I have?
About 20 minutes, right? Supposedly that's
okay.
Yeah.
Yep. Thanks. So just to give you an example, this would be an example of how you could go about a computational challenge. This is a simple one-dimensional setup of a grid, where I have taken my grid, these crosses here, and I've split it across two processors here. Now, if I'm starting at time equals 0 and I want to go forward one step in time, if I'm doing finite differences, say, then I would use these 3 points to compute a derivative. With that derivative, I can update the value of the point up here. So far, so good. The problem is then, for example, this green cross here, where if I go down, I don't have a point to the left that I could use to take derivatives off, so I don't know how to update that point. So that would stop my attempt to run on multiple processors right here, because I couldn't update that point. The solution there, of course, that people have come up with a while ago, is to actually make extra copies of the points and basically take the point that would be here and have it present on both processors. And then you can update everything that you can. And then once you're done, you can get the missing data from the other processor in these blue ones. And that's called a copy. It's called a ghost zone exchange. And it's a communication step that you have to do. And this is doable. You can do this if you want to as an exercise in a tutorial. If you write this in Python or so, this is easily doable in whatever, something like a 2-hour time frame or so. If you have somebody to help you how to do it. Doable. You could actually get a PhD out of this maybe 20 years ago. No longer is this the case today, but it's in principle doable. You can also do this in 2D. It looks pretty much the same. It gets a little bit more complicated because now you have kind of these regions here and these, which are kind of what you had before. You have the neighbor over here. Now you also have to worry about these corner cases where you have more than one neighbor. So you can see there's a little bit more complexity that comes in there. So already this is harder. You can still visualize it in 2D. You can draw it on a piece of paper. This is all still somewhat doable. This, of course, is not what you want to do in the end. A real system will more look like this. So this is the llama grid in Cactus, where you have multiple different coordinate systems. You've got these curvilinear ones on the outside. And then you've got Cartesian ones in the middle. There is this funny overlap here. There's mesh refinement in there. So you can see that there's a whole lot of infrastructure work that you have to do to make this work. And if you do any other code and any other formulation, this will look very similar. If you're doing a spectral code, you'll have the same thing. You have multiple domains, you have to communicate them. This doesn't go away. So there is a lot of just non-science work that goes in there to make these things work well. And I mean, non-physics science, right? There's computer science in it, but maybe not physics science. All right, so the Einstein Toolkit tries to address a lot of these with different components that have been developed over time. This is the same slide as before. This is the same gorilla. Now only there is a couple of solutions in there to some degree. So to make use of vectorization and proper SMD, SIMD instructions, we try to use automated code generation, which means that the somewhat unintuitive way to use vectors can be hidden away from you by the code generation software. And there's 2 that are used in the Einstein Toolkit. One is called Crank, that's Mathematica based and was used initially to generate space-time evolution codes. And the newer one is NeurP+, which is Python based and has similar functionalities. We use OpenMP to scale to many cores on a single node. That's traditional. We scale to many nodes using MPI, which is what 90% of all the codes are also doing. There's a very few that do it otherwise. It could be used, so the spectral code in particular is one that does it differently, uses the Charm++ framework. but the majority is MPI just because this is somewhat like the industry standard. It's also used by what we call drivers, Carpet and Carpet X, that actually do the heavy lifting for you so that the science code doesn't have to worry about it. They just know that the data will be there when they need it, but they don't have to worry about the minutiae of making that efficient. Adaptive mesh refinement is also done by these drivers, Carpet, Carpet X, and then the time stepper. Traditionally, the method of lines, time stepper, but other ones work as well, have to be involved a little bit as well. But again, this is something that the infrastructure provides, not the science code. All right, GPUs is new. This was attempted a couple of times in the Einstein Toolkit with some success, but never quite made public. The new driver, Carpet X, is really geared towards GPUs, and it's one of the major goals to have efficient GPU support in there. And there's now a number of codes that are using it somewhat efficiently, both developed here and some in Europe and some otherwise in the United States. So this is the way to go, and it seems to finally work. And then other things, machine learning is being used for various ways, and there's groups that are looking into incorporating machine learning methods into the Einstein Toolkit, and that are worrying about how do we make this such that others could use the same thing, so that not everybody has to reinvent the same wheel, and more complicated things maybe. All right, so go through. So there's other challenges as well that aren't maybe so obvious, but will bite you if you try to run the code at a large number of processors. I/O suddenly becomes important. If you take 5 minutes to write your data files, this will be troublesome. If your files are easily corrupted, then you're in trouble. You will have to run longer usually than the cluster lets you. You might have to run for 6 months, but the cluster only lets you run for 24 hours. So you have to have a way to checkpoint and restore your simulation state in a way that you trust it. So you don't necessarily want to implement it yourself, only to find out that you forgot to save a random seed, and you're no longer able to reproduce your run after 6 months when the reviewer asks you for specific detail of your paper. So this is something that you want to have in there. All right. So what are the challenges doing this? So again, if you want to go from one green dot to many green letters, how do you do this? In some sense, it's easy if you can concentrate on just the infrastructure and you have different science interests, because then there is no science competition and people are very happy to collaborate on the infrastructure. And if you do that, then, well, this works. You provide infrastructure for the science code. MPI is an example for that. NumPy works like that. Everybody can use it because it's such a basic infrastructure. You can build a community around the infrastructure and hopefully have that one grow with time. All right, so such a community then will have to use tools. These are kind of the ones that the Einstein Toolkit uses. So we have mailing lists, phone calls, telecons by now, a website, we have a wiki. We use Git extensively, and other version control systems were used in the past. So there's a technology in there that you have to provide, not just the knowledge, but also just host a web server somewhere, which requires a bit of work. All right, now then, if you don't have the situation where you have different science interests, but everybody does the same science, does this still work? And in principle, yes, it should. You're still collaborating on the infrastructure, but everybody wants to share. So this is doable, but it gets politically a little bit more dicey, of course, because suddenly you have competing groups collaborating. But this is doable, and the Einstein Toolkit has been successful in actually doing that. And we do this by having standards, how to collaborate, and how to make different modules talk to each other. Which one you pick doesn't matter so much. If this is your beef, you're free to pick the imperial units. You can also pick metric units. They do the same thing effectively, as long as you're careful to know which unit you're using. If not, you may crash land your lander on Mars where you shouldn't crash land it. So this is kind of the same thing in software. Right. So for the Einstein Toolkit, it means that we have to support multiple tools, different programming languages that people would like to use, C and C++. Fortran is also a language that's still very much alive in scientific computing, and it's still a good language to use if you're doing heavy number crunching. But also more humdrum stuff like some scripting, Perl or Python, and different operating systems, mostly Linux on the supercomputers, but on your desktop system, it's probably going to be Mac or Linux, or maybe Windows as well. So different flavors of operating systems have to be supported. Right, and very important for scientific publications, you want to give credit where credit is due, ideally in a way that automates this thing. You don't want to have to go through hundreds of pages to find out what to cite. You want to have a concise location where it says, if you're doing this, please do cite such work. And that helps a lot. It means that somebody who contributes a module is more likely to actually see their efforts remunerated. All right. So, which time do I have? Steve, Joseph, how much time?
You have 15 minutes.
That much more? Oh,
If you want that.
I mean, way faster than I thought. Okay, so does this work? It worked. It worked in the past. It still is working. We have quite a number of researchers in the United States, in particular, that have been active there. This is partially historically true because part of the Einstein Toolkit was developed here, but also other countries are active. This is a little bit centered towards, say, Europe and the United States. That's not quite true as far as users go. There's a lot of users, in particular in Asia, in Eastern Asia and Southeast Asia, that aren't listed here to some degree because it's the other end of the world. So most of the communication actually happens to European Einstein Toolkit users, but there is an active community there that is growing and grows a bit, grows as well because the Einstein Toolkit is free. So users in universities where there isn't traditionally a numerical relativity group can still use it without having to have a lot of local support. So that's the big benefit. But that's basically what it is, and it has been used successfully by different groups, and hopefully will be in the future. All right, so, and let me summarize what we have for the Einstein Toolkit. So the goals of the Einstein Toolkit as spelled out on our website are actually that it's supposed to be a community-driven framework that provides core computational tools for numerical astrophysics, and it should be a general purpose tool. So it's not just one particular problem that we want to tackle, but we want to provide tools for different problems that you might be interested in. It has different large components that traditionally are used. The main thing traditionally used to be the Cactus computational toolkit. That's the heavy lifting thing for the large-scale computer simulations. Then there are things that help make your life much easier. There is something called a simulation factory, which at one level is a database of existing compute clusters and how to use them, so that if you want to run on a cluster, say in the US Access framework, you don't have to look up exactly how to run on that cluster, but it should already be in the database. Ideally, you just download your code, you run compile, and then it compiles the code, and you can submit the simulation right away without having to first study the documentation to exactly see how to run on that cluster. Ideally, also in a way that's efficient on that particular cluster. It relies a little bit on help by the actual users that keep these clusters that they use up to date. Then there's code generation frameworks in there, Crank and NeRPi+, that are used to translate these complicated equations, be that general relativity or maybe hydrodynamics equations, into executable code that then can be fed to the compiler and compiled. And those help a lot, in particular, if you want to explore different things rather than just what's already in the toolkit. And so if I want to play around adding extra terms to the Einstein equation, and that might be science equations, or I might be interested in adding a different way of implementing boundary conditions. It's much easier if I can do this on a level that more or less resembles mathematical expressions, rather than having to go down and hand code the SIMD instructions that the computer actually executes. So it's a large help. And then, of course, the science modules that go in there that should cover what's currently of interest to the community with efficient and well-tested codes. The guiding principle for all of these is that it should be an open keep talking. Should be an open framework, both open in the sense that you can just download the code, but also all the decisions and discussions should happen in the open. So we don't want to have backroom deals where a couple of people get together and decide what the toolkit will do in the future. We want this to happen in the public. We do this in the public Einstein Toolkit calls. We do these with discussions with the community at meetings like this. So it should be something where you know what's going on, and it's not somebody's pet project, but it's a community-driven effort. We want to provide good interfaces that let you plug in different modules. And we want to have a separation between physics and computational infrastructure, just because traditionally these two levels of expertise have been in separate persons, right? You were either somebody who's good at the physics, because this is what you're studying, this is what you've got your PhD in, or will be getting your PhD in, or you might have spent 10 years developing a really fast infrastructure to communicate between 10,000 nodes. Both you'll need, but it might not be in the same person. Right, and we want the code to be production ready. That's visible in our gallery examples that we have on the website, where we have a couple of typical applications that you can download and run. And while the gallery example itself might not be quite state of the art, it should be able to turn it into state of the art by the turn of the knob, maybe increase the resolution or something like that. And you want to have high quality code. That means the code in the Einstein Toolkit should be understandable to somebody who wants to edit it, and it should have documentation, comment, and whatnot, so that you can actually build on it, and it's not just a black box. All right, then let me kind of show you how this grew in the past. So initially, Cactus really had some infrastructure and essentially one application code or so. But then since this worked, there were more application codes that used it. So now suddenly you have the one infrastructure puzzle piece in there, the gray one, and you have more application codes around. That means that now if you add extra infrastructure facilities there, then all of these application codes benefit from that. So you get an improved benefit. It's not just you do some work and then one person benefits, but you do some work and then 10 persons benefit. So that helps incentivize infrastructure development because there's a bigger return. All right, that then becomes a positive feedback loop. You get more science areas that want to contribute to it, that use this infrastructure because it's useful, and the whole thing should grow. The nice thing about the Einstein Toolkit, and that's maybe different from other numerical astrophysics code that you can find out there, is that it is from the beginning designed to be very modular. It's not a monolithic piece of code that some group develops and every once in a while they throw it across the fence and you can use it. But it's a set of modules that are designed for distributed collaborative development. It means that some pieces of it can be closed source, some pieces are open source, and that's perfectly fine. That's by design. We want this, right? This is the only way this works. You will have to get your PhD or your papers out with your science code that you've spent time developing. You want to do this on your own first and then reap some benefits, and then maybe afterwards you may want to make it public. So this is by design. And so we want this, and this is, I think, one of the things that makes the Einstein Toolkit unique, that this is built in from the beginning. You can do this, and you can easily change out the infrastructure to the new version and keep your science module at the old one and get the benefits, at least if it's written reasonably well. All right, so let me show you how this works. This is the Einstein equation again, this time with G's and C's in there, but it's the same equation that Alexandra showed you before. Now, these split up in different things. G describes space-time curvature. Then you have the constants that are in there that maybe are some things that hopefully don't change, but every once in a while, maybe you want to tweak them. And then you've got the matter constants on the right. If you want to simulate these things, you want to somehow put these into software concepts as well. This might be complicated on the matter side in the sense of that matter might not be just matter. I mean, GR only cares about matter, but there's different sorts of matter that you might want to care about. Maybe you care about hydrodynamics, electromagnetism, or maybe scalar fields or particle radiation, neutrinos, or God knows what else, or cosmic rays that come in. So there's different things that would fall under matter. All right, so then let me see, how does this look like if you look at code? So we try to have these modules that we call base modules that really don't do anything other than provide an interface. We have a module called ADM base, which will describe to anybody who cares what space-time looks like. We have a module called TMU base that lets anybody who cares look or describe what the matter content looks like. Then there's evolution modules that will use these. For example, the McLaughlin code, MLBSSN, is a code that can involve space-time and then report back its results in the ADM-based variables for anybody else who wants to use them. And it will use the TMU-based data to get informed about matter. It doesn't care what the matter is, if it's hydrodynamics, scalar fields, whatnot. It really only cares about community. So the minimal coupling that you have in science is present here in the computer science. Similarly, for say matter ones, as an example, we have the GeoHydro code in here, which was the first matter code present in the Einstein Toolkit. It will provide its answers in the hydro-based form, so that anybody who wants to do analysis can use these variables in hydro-base, which have a well-defined meaning. They're always going to be the same, no matter what GeoHydro wants to do internally. And then again, it will use ADM-base to get information about the metric and the space-time, and it will return the energy contents of its variables in TMU base. So this is how these work together. And this has been successful because it lets you have initial data and analysis codes that don't have to know anything about what's going on down here. They only need to know what the ADM-based variables look like and what the hydro-based variables look like. So that's the modularization that you want, so that you can use 2 punctures for your initial data for black holes, or you can use 2 punctures binary black hole scalar field, or you can use FUCA, and they all work with anything in here because they only talk to ADM base. Similarly, an analysis code only looks at hydro base or at ADM base and can detect apparent horizons for black holes or the total mass or outflow of material for everything that's in there by just looking at these. That's the idea. And the good thing is that this actually worked. We have now not just one space-time evolution code in the Einstein Toolkit, but at least 3. There's the McLaughlin code, there's the Lean public code, and there's the Baikal code, which all can involve space-time, but they do it slightly differently, and they're coded in different manners depending on what people would like to do. There's also 2 different matter evolution codes, GR Hydro and Illinois GMHD, that both work. And you can choose either one of them, and basically, if you don't like one, you can at runtime even change it out for the other with very minimal changes. And it turns out that this worked really well in that when the Canuda framework was added to the Einstein Toolkit, it added some completely different sort of matter to it, namely Crocker field, that aren't anything like hydrodynamics at all, but they do fit into this framework really well in that they feed back into TMU base, and they get the matter the space-time quantities from ADM base. So this really worked well in that you could add extra fields that weren't even thought about initially to this framework without problems. And users here, if there was trouble, then they can speak up and say what was troublesome. All right, so that's the idea. Let me restate the guiding principles. We really want to have an open, community-driven software development going on. We have a separation between physics and computational infrastructure in there. We want to have stable interfaces that allow you for extending them as you want, but also let you be sure that the code that you started your PhD with still has a good chance of working 3 years in, and that you don't constantly have the rug being pulled out from underneath your feet because the basic infrastructure changes every 2 weeks in an incompatible way, and you spend all of your time catching up with the infrastructure. You can sum up now. I will. So this means we want to simplify usage where possible. It turns out that, of course, doing science is more than just running simulations. We can't teach you how to do science or how to do physics. That takes longer. But we can make sure that you have time to learn so by making everything else easier. And that's basically it. I think so.
Okay, thank you. Now, we have an opportunity to ask a question or two. Please do not type a question in the Zoom as I won't see it, but if you could type it in Slack, I will. So, or if you're in person and you have a question. Any questions? Yes.
I was curious about the use of machine learning, what your main ideas, including machine learning in EPK.
Okay, so I mean, there's 2 ways, I guess, that I have seen it being used. So there's one way that this has been used is to try and simulate subgrid physics. So if you're doing hydrodynamics, then you have turbulence, and you might not be able to fully resolve the turbulence length scales. And you have to come up with a model that models what's going on in these cells that they can't model. And machine learning might be a way of doing that, similar to coming up with another way of modeling it. You could also use it as a speed up for certain pieces. There has been work of using machine learning methods to speed up the conserved variable to primitive variable inversion in hydrodynamics codes. That basically is a root solve that you could possibly speed up, or to speed up equation of state lookups. So this is something that you can do. You can use it at the end, of course, for anything that's data analysis related, right? So LIGO has been looking quite heavily into using machine learning for detection, and that you might be aware of. That's kind of at the back end, not directly in the Einstein Toolkit. And then there's other things, right? Now that, say, natural language processing is getting good with machine learning, it might be something where you could look into, oh, could you actually come up with something that lets you specify in words a parameter file that you want? And then the code could generate that for you, because that's one of the big problems that you have. If you start from scratch and you want to start a simulation, the answer is usually take a working one and modify it. So that might be something that one could look at, completely independent of actually using it in the high performance computing.
You can ask ChatGPT, what gauge should I use?
Of that sort, right? That the problem is the fact that you can't make any mistakes, right? It's not like English language where if you get a word wrong or so, humans will fix that. If you tell the computer one wrong line in your parameter file, it's wrong, but who knows? But you have a course of mathematics.
Yes, I do. But it's also terrifying, so I think the questions are
I'll answer this. Okay. So, Steve, any more questions or?
No questions online, so I think you're done.
Thanks.
And-
There are questions online, actually, on the chat.
Okay.
Yeah, I'll answer
I
those
can't
online.
see them, I guess.
There's also a question in Slack, actually.
Where are the questions?
Okay,
I think they have them in the Zoom chat.
Do any
Yeah,
of
that's
the
right. Yes.
evolutionary codes incorporate constraint damping?
we do. There is a CCZ4 version of McLaughlin that would do that, and I think other groups are also looking into adding this. Yes, we do modified gravity theories in nonlinear models. I would probably refer you to the Canuta developers because this is their area of expertise, and that's in the Einstein Toolkit. But I'm not an expert. I think I'm being booted out here.
Oh, okay.
Just quickly, what did?
I was just gonna ask, is there any component of it that makes it not a very good fit for high throughput computing clusters?
Oh, sure. You can always do that. There's certainly things in there that make it hard to use. Basically, it really is designed to have exclusive use of a node. In high throughput computing, if you're only giving a core here and a core there, then your computation costs become much more important.
No, like dedicated clusters where you can have entirely dedicated machines.
Yeah,
Because it has open MPI and it can interact with it.
you could use it on an HTC environment that way, as long as it looks like an HPC environment, basically.
All right, let's thank our speaker again.